I prepared my presentation in English, but okay, we'll see. Okay, as I'm in the beginning of this workshop, I wanted to do something like an overview, a general overview of the main sources of uncertainties that we can find when we do an estimation of the biomass, and especially the above ground biomass. So we can see. See. Okay, this is a little bit the contents of the presentation. So we'll have an introduction, then I will talk a little bit about the first type or sources of uncertainties. Then I will try to provide some recommendation based on the scientific literature. Okay, this is a little bit the standard method that it's used for biomass estimation. So we start with measurement of trees in the fields. So the main parameters that we measure can be ODBH, something like the diameter, the height, overall density, but we can also measure some additional parameters, can be crown diameter, etc. Then we have to select anolometric equations to convert these parameters measured in the field in biomass or in volume. Then we do the sum of the biomass of the tree, then we do an average of the biomass over the plots. Yes, the main problem is that that uncertainties is rarely evaluated and rarely reported. So this is also my experience, because as you can see, some example of this is just to provide the order of magnitude of the uncertainties that is associated with above ground biomass estimates. This is a table from the guidelines of the PCC of 2006. So you can see that here we have the ecological zone, the continent, and then this is an estimation, it's a default values from PCC of the biomass. And we can see that also the PCC don't provide an exact value, because of course it's impossible to provide an exact values, but provide the values with some uncertainties. So we can see that sometimes this uncertainty is quite huge, can be quite huge. For example, in our case, we can check for tropical rainforest in South America. So we have a range of variation that is from 120 to 400 of tons of biomass per hectare. So the uncertainties is considerable. This is another example. This is a study that was made by Schaaf in 2004. And this is one of the most complete studies that were performed on this topic. And we can see that also at the end of the study, the result was that the standard error on for the estimate of the biomass for 1 hectare is about the 24% in percentage on the mean. So this is a little bit the order of magnitude of uncertainties that we have to face when we do an estimation of the biomass. So the first sources of uncertainties when we do an assessment of the biomass are related to the step of the estimation. So we can see that these 4 steps are the same that I showed before. So there's the step of the measurement of the tree, then there's the steps of the choice of the allometric model, then there's the problem of the size of the sample area, then there's the problem of the representativity of the plots. So in every step, in every one of these steps, we can see that the error is propagating just step by step. Okay, we will analyze the first source, that is the source of the term measurement. So, but this is a bit a generic overview. I mean, no measurement made is ever exact. and it depends, of course, by the apparatus used, by the skill of the observer, by the experimental technique used. So the error is the deviation of the set-bed value from the true value, or if we use the IPCC definition, is the lack of knowledge of the true value of a quantity. For example, so every measurement is also given, the normal is given in this form, so there's a value and there's plus minus a certain amount. Okay, during the true measurement, during the field measurement, of course, the error can be in the diameter measurement, in the height measurement, in the wood density measurement. I just put these ones because are the most used ones. Okay, I didn't focus so much. I will not focus so much on this kind because at the end this is be considered as a random error. So normally this error is an average out at plot level, because summing all this error we can see that it's an average, so it can be negligible. It cannot be considered. This is of course not completely true, but for our purpose maybe we can just skip this part. Okay, this is the second source, that is the choice of allometric model. Of course, the quality of the allometric equation used for the estimate is very important for ensuring the accuracy of the forest carbon estimates. And that's the study that is from Melson et al. Of 2011 that says that model selection error may introduce from 20 to 40% of uncertainties into a laboratory carbon estimate. So I think we can consider this step as the principal source of uncertainties when we do biomass assessment. Of course, the development of biomass equation is laborious, is expensive, and time-consuming process. So this is one of the main challenge that we find when we try to develop an allometric model. Of course, the best solution should be to have an allometric equation that consider for every ecosystem types, and not only for tropical rainforest. Okay, of course, there's a limitation in the availability of allometric equations because there's many issues on this topic. For example, that especially in developing countries can be unlimited access to international journals, so that is when most part of the allometric equations are published, so this can be a first kind of limitation. And then many allometric equations are not published in international peer-reviewed journals, but are stored in some local libraries, maybe the library of the ministry or the library of the Forest Institute, etc. And sometimes when the equation is provided, sometimes the metadata are not reported. So it's difficult to compare the different allometric equation and to assess the quality of the allometric equation. Okay, this is again about the choice of the allometric model. There's an error that is associated with the model. It's about the statistic of the regression. I will not discuss about that because I've seen that there's many presentations that will discuss this kind of issue. But I will talk more about the error that is associated with the choice of the model. So the possibility that we can have is that we have more than one equation for an ecological zone, for our forest, or we don't have any allometric equation. So, okay, this is the same study that I was talking before of Melson 2011. We see that just because of the choice of allometric model, when we can choose between more than one allometric model, the estimation can vary from the 20 to the 40%. So we try in fact to also to assess how much the variability, the choice of allometric model can affect the estimate. So we take the case of the 3 1-hectare plots in Ghana, and we used 4 different allometric equations to assess the same forest. 2 pantropical equations that is the most used one, the one from Brown to 1989, the one from Shav to 2005. And then we also tested 2 regional equations to developed for Africa. So the one from Henry et al. 2010 and the one from Jomo that were developed in Africa for the same type of forest. And this is the result. So every option, every one of these bar is an estimate. So using the first option, we have an estimate that is about 290. And using the fourth one, we have an estimate that is 135. So, and this red dot are the PCC default values. So we can see that all the estimates are within the range, more or less, of the PCC default values. But of course, there's a big variability in the estimate. And this is just because of the choice of the questions. Okay, how can we choose about different allometric models? Of course, there are many criteria that we can use. Of course, the first one can be the model quality. We can check the range of validity of the model, its capacity to extrapolate prediction, etc. Then the specificity, of course, because there's equations that are developed just for a local use, and they're more generic equations, something like the equation from Shav 2005 that can be used, that are supposed to be pantropical, so to be used all over the tropical forest. And then, of course, one important parameter is the size of the data set used for the model fitting. Of course, if an equation is developed starting from 5 trees, we can suppose that the quality is not so good. These are some statistical criteria that can be used to test the quality of the model fitting. This is something a little bit statistical. We can check the bias, the R-square of the regression, the key information criterion. The problem is that many times these data are not reported with the equation, so we cannot judge the quality of the equations. Okay, these are the main problem that we face when we try to apply an allometric model to a tropical rainforest, because most part of the equation are constructed from a limited samples. Sometimes they are applied beyond the validity, the diameter range, and they don't take into account normally one important variable, that is the wood specific gravity or wood density, for example. This is the same study of Shav 2004 that shows that with allometric equation construct from 50 trees, the standard error of the mean was 10% of the mean of the above regarded biomass. So the result of the study is that it's always better to have equations developed with more than 50 trees, and this is so we can keep the standard error of the mean of the estimate within this range of uncertainties, the 10%. If you use the allometric equation that are developed with a lower sample size, we can have some problem. Okay, this is to show, this is a project that we did with FAO in collaboration with the Tusha University and CIRAD. This is a little bit, we try to solve the issue of where there is no equations available at a country level. So this is a database, a collection of allometric equations that we try to collect all the allometric equation available in literature, in the report. So this is freely available. You can access here to this website. And at the moment, the database that we developed include more than 6,300 equations. We can see this is the distribution of the question, of the place, of the location where the question were developed. So we can see, and we did this in collaboration with Katy as well. That was one of the main contributors that Katy worked for to collect the questions for South of America. Then we, of course, we are also we also worked with regional institutions in South Asia and in Southeast Asia, Africa. So we can see all this information are freely available to the internet. So this can be a way to solve the issue where if you don't know if an allometric equation is available for your forest, for your country, for your ecological zone, you can check here before and see if there's something available. Okay, of course, to choose between allometric model, there's many criteria, but maybe I can skip this part as maybe it can be discussed afterwards by some other. I mean, we can use some decision tree to check some algorithm to find the correct allometric equation, but maybe it can be discussed afterward. Okay, we can pass to the third source of uncertainties during a biomass estimation. It's the plot size. I mean, of course, in this step, the source of uncertainty can be related to the accurate estimation of plot size, to the trees missed when you do the field measurement, to a double measurement of the tree, or instead to a tree assigned to a wrong category. I mean, for example, you can consider one dead tree, you can consider it alive, and so assign this tree to a different pool. Okay, so the main question is better to have a few big plots or many small plots, and which is the minimum plot size? I will try. Okay, the forest plot normally range, this is not very, from 0.2 to 100 hectare. Okay, of course, 100 hectare is a very big plot. The main problem is that the spatial distribution of biomass in tropical forests is that the few big trees contribute to a big fraction of total biomass. So if the plot is too small, we have to be an underestimate or an overestimate of the biomass at a plot level. So we can see this is, for example, some data from Ecuador. The diameter of the cycle is proportional to the above ground biomass. So we can see that there's big spatial variability in a tropical rainforest. This is another example. We can see that, for example, that this can be considered as a tropical rainforest plot. And also here we can consider the diameter of this cycle is proportional to the biomass of the tree. If we take this plot here, we have an overestimate of the biomass at a plot level. If we take the southern plot, we have another estimate. This is another example of a tropical forest from Cambodia. We can see the distribution is not very homogeneous. So how we can solve this problem? We did a study. The fact is that by reducing the size of the plot, we expect a bigger variability in the estimates. We try to check if this is true by using the same data. This is 9 hectare forest in Ghana. So we tried to reduce progressively the sample size of the plot from the same forest, and then check how this can affect the estimate at the plot level. So we analyzed 4 different sample size. That this is the 1 hectare sample size, 100 per 100, then 50 per 50, then 20 per 20, then 10 per 10. Okay, this is the estimate of above ground biomass in tons per hectare that we can have by using the different sample size, the different size of the subplot. So if we use a subplot of 10 per 10 meters, as we can see, we have a big variability of the estimates. The estimate from close to zero from this point that is about it's about 5,000 tons per hectare. So of course it cannot be true. If we take a subplot of 20 per 20 meters, okay, it's a bit better because the distribution starts to be more close to the normality. Then, okay, 50 per 50, then this is the distribution that we have to taking the subplot of 1 hectare. So, more we reduce the size of the plot, more variability we find. This is a summary of the same data. We can see the standard deviation, it increases proportionally with, in inverse sense with the sample plot size. Of course, if we check these parameters that are related to the normality of the distribution, we see that one quarter a hectare plot is the minimal size that satisfies the normality criterion. So this result is consistent with the result of SHAV of 2004. So I think this can be interesting. This can be considered as a recommendation. So with plots that are smaller than 50 per 50, you can find some problem. Okay. But we also see that also between the 1 hectare plot, the variability was high because the minimum of the above ground biomass estimate per hectare is 277, and the maximum was about 500. So also if we take a big plot, there's a big variability in the biomass estimate, and this can be explained by 2 reasons. Of course, the sampling error in a narrow sense, of course, because if you take, whenever you take samples, of course, you have a different estimates, but also a special variation in above ground biomass because different parts of the forest are really different. So this should be taken into account, into consideration. So. And this leads us to the fourth source of uncertainties, that is at landscape level. So how can we know if our plot is representative of the forest of the region? So these are the main factors that affects the variation in the forest structure at the landscape level. Of course, it's intuitive a little bit, but it depends. Of course, this factor is the soil type, the topographical position, the slope angle, the patch size. If there's some tree falls, there's some area with a lack of tree, etc. The plot age, that it's a parameter that, of course, is difficult to evaluate normally, especially if tropical rainforest is impossible. This can be used for a secondary forest or for a plantation. Then if we raise the scale of the landscape, of course, the main factor are rainfall and length of the dry season, okay, its climate in general. This is another case study from this article of Lemonnier et al. 2010, and well, they made a network of small survey plots laid down approximately every 100 meters along a transect perpendicular to a topographical gradient. So if we see the results here, so this is, if we see the number 1 is at the valley, 2 is lower slope, etc., is the topographical gradient, we see that the topographic situation and geology which affects the structural variables of the forest. For example, the stem numbers, the basal area, and above ground biomass. This is another study of Clark of 2000, and also the result is that both soil type and topography which affected stem number. Steep slopes on multi-soil average 44% more stem per hectare than flat in steep soil plots. Okay, this is the results, but it's just to show how the topography can affect the above ground biomass. This is another study that puts in relationship the above ground biomass with the soil, the nutrient of the soil, and we see that biomass was positively associated with some nutrients, like potassium exchangeable base, and negatively associated with zinc, with aluminum saturation and fine sand. The correlation is not strong, but it's a result, so we can also take this into consideration. This is another. So some recommendation that we have to take into account when we try to put our plots in the landscape. That should be better to do preliminary reconnaissance to identify the major habitat gradients of the landscape. So it should be better to understand if there's some. Okay. Yes, because it's a big topic. So the geohydrologic gradients, the nutrient-based gradient, and topographical gradient. So this is the result of another study. The data suggests that a total sample size of 5 hectares or 20 plots of 1/4 of a hectare can allow a landscape estimation of above ground biomass with an error of 10% in percentage within a 95% of confidence. These can be some additional sources of error when we deal with this kind of study. So, of course, just some error in data entry, some mistake when in data entry, then some mistake in the definition, because sometimes the definition are not clear what's above ground biomass, if should include the stump, should exclude the bark, etc. Then this is more related to the allometry when you perform your regression. If the equation is log transformed, you have to use a correction factor then to use your result. Okay, this some recommendation is a little bit what I already said before, something like double check the plots that containing many large trees, then to try to include only plots larger than 1/4 hectare, then avoid biomass model with a sample size lower than 50 trees, then use equation only within the interval of applicability, then try to include the wood density as a variable if it's possible. Then we should also try to include in the estimation also some life form which are different from trees, if they especially if they have a diameter which is bigger than 10 centimeters, and then investigate the landscape variability at landscape level. So this is a bibliography that I use, some basic bibliography with all the study that I checked for this. They are available also. I have with me, I printed if you want to check, to verify. Well, it's finished.
Secretaría de Medio Ambiente y Recursos Naturales.